Hello students, in this video we're going to talk about the trapezoidal rule. So let's get started. So in here we're going to do trapezoidal approximations. So very similar to when we did Riemann sums when we used rectangles, trapezoidal approximations are going to use rectangles to approximate the area under a curve. So when we have a partition on a closed interval from A to B, and we split that up into n subintervals of equal length, this is the height of each trapezoid. So that height is defined by h equals b minus a divided by n. And then we have the trapezoidal approximation is h divided by 2 times this parentheses here. Now notice that y sub 0 is our initial height, and that should always start at your lower limit. Y sub n at the end is the y value of your upper limit. And in between, this is where we split them up into the n subintervals that are given. The other thing that's very important to note is your first value is just going to be left alone. It's just the y value of your lower limit. The upper portion is the upper value or y value of your upper limit. In between, though, we are multiplying by 2 to each portion of the function. This only goes for the inner portions. The two outer portions should not have the 2. It should also be noted that the RRAM plus the LRAM divided by 2, or the sum of the LRAM and the RRAM divided by 2, is equal to the trapezoidal rule. But since we're working on the trapezoidal rule, we're going to go ahead and use that formula. So let's try one now. So here we have the integral from 0 to pi for sine of x dx, and we know that our n is equal to 4. So let's go ahead and find our height. So h is equal to b minus a divided by 2, which means that h is equal to, not 2, divided by 4, because it's b minus a divided by n. So h is equal to pi minus 0 divided by 4, which means our height is equal to pi divided by 4. So now let's go ahead and look at that formula, which says t is equal to h divided by 3 times the other stuff, which I'm not going to retype because I don't want you to waste your time watching me retype the original function. So we know that our height is pi divided by 4, and then now it's divided by 3. Next portion is to figure out our f of 0 plus 2 times f of, this is the portion that I didn't specify, which we're going to go over now. The next thing should be f of pi divided by 4. And what we're doing here is we took our, basically our height, because we split them up into 4 equal intervals, and we're finding the height of each one. So because our h is pi divided by 4, we start off at our lower limit 0, we should end up at our pi. So, in moving forward, we're going to have plus 2 times the function 2 pi divided by 4. Notice we went 1 pi here, 2 pi here, and keep in mind I'm also adding these 2's because that's what the formula states, plus 2 times f of 3 pi divided by 4, plus f of 4 pi divided by 4. Notice I did not put another 2 here because 4 pi divided by 4 is just pi, which means we're at the end. So we're going to go ahead and simplify a little bit. This turns out to be pi divided by, I did it again. Sorry guys. This 3 should really be a 2 because it's the trapezoidal rule and not the Simpson rule, which we're going to talk about in a second. So this should be pi divided by 8 times f of 0 is just 0, plus 2 times square root 2 divided by 2, plus 2 times 1, plus 2 times square root 2 divided by 2, plus 0. Get pi divided by 8 equals, when we simplify it, 2 square root 2 plus 2. And when we multiply this out on our calculator, we get 1.89612. So that's the trapezoidal rule. Hopefully it's not so bad. Just make sure you're careful not to confuse it like I just did with the Simpson rule. So let's look at another example. Now, real quick, problems with trapezoids. Use the straight lines to approximate curves. Now, when we do the trapezoidal rule, it overestimates if the graph is concave up, and it underestimates if the graph is concave down. So just something to keep in mind. When we're estimating with parabolic curves, instead of using straight lines to represent curves, we can use parabolic arcs, as you see here. Fortunately for you, I want to make sure we just talk about it, that this is another method. I'm not going to ask you to calculate it. Simpson's rule, however, I will. So notice the difference between Simpson's rule and trapezoidal rule already is that instead of h divided by 2, it's h divided by 3. The other thing that's important to mention is our ends still stay the same, just like in trapezoidal rule. However, in the Simpson rule, we're alternating between 4, 2, 4, 2 until we get to the end. So whichever one you leave off at, whether it be a 2 or 4, that's okay. Just so long as the two ends are 1 in the front, and then we're alternating 4 and 2 with 4 first. So let's try a problem now. So here we have the same exact problem as we did before, but this time we're using Simpson's rule. So we're going to use our h. H is equal to pi minus 0 divided by 4. So our h is pi divided by 4. So we know that. So since we're doing Simpson rule, we're going to have our h divided by 3. For real this time, not 2. And we're going to have our middle. So we know that h is equal to pi divided by 4 divided by 3 times f of 0 plus 4 times f of pi divided by 4 plus 2 times f of pi divided by 2 plus 4 times pi, 3 pi, sorry, this should be 4, plus 4 times the function 2 pi divided by 4, sorry, and this should be 3 pi divided by 4 plus f of 4 pi divided by 4. Again, this simplifies to pi divided by 12, and f of 0 is 0, plus 4 times square root 2 divided by 2, plus 2 times 1, plus 4 times square root 2 divided by 2, plus 0. So when we simplify this again, our answer turns out to be pi divided by 12 times 4 square root 2 plus 2. And finally, we get 2.00456. So notice this was a lot of plug and chug. And if you compare this to the answer we got for trapezoidal rule, they're fairly similar. It's 1.89 versus 2. So it is within a 10% error, so we're okay. So let's try another one, but this time we're going to use it with a function that does not have sine or cosine. So let's try that now. So here we're going to do Simpson's rule again. This time we need to find our height. So our height in this case is b minus a, so 4 minus 0 divided by 4, because we are doing it in 4 equal intervals, so h is equal to 1. Now looking at the formula here, we basically have 1 divided by 3 times f of 0 plus 4 times f of 1 plus 2 times f of 2 plus 4 times f of 3. Notice we're getting these values here, the 1, the 2, and the 3, basically from our h, and we're adding up until we get to our upper limit. Plus, typically we would have done f of 4, but because 4 is our upper limit, we're going to go ahead and delete that and close that up. So we now have 1/3 of 0 plus 4 times 1 plus 2 times 8 plus 4 times 27 plus 64. This becomes 1/3 of 192. And finally, we have 64 as our final answer. So this is how you do Simpson's rule. Shouldn't be too bad. And notice I did all of this by hand, except for the square root stuff, to be honest. So finally, because we did Simpson's rule and we did trapezoidal rule, these are all just approximations. The most exact answer you're going to get is by integrating using definite integrals like we've been doing in class. Since they did not give the exact answer, they do have some error. And so the amount of error depends on several variables. So let's take a look at what that would be. So here's where you have these error bounds. The absolute value of e sub t is less than or equal to b minus a divided by 12 times h squared times m sub f double prime. And then you could read the other one for the Simpson rule on the right, which is the e sub s. So the e sub t is the error of the trapezoidal rule. E sub s is the error of the Simpson rule. H is the length of each subinterval. The double primes refer to the maximum value of the double prime and the fourth prime, respectively. Fortunately for you, you don't have to calculate that. You don't have to worry about it. I just wanted you to see that because we're doing Simpson and trapezoidal rule, there are going to be some errors. So that's all for now. I'll see you guys next time.